Biomass Magazine webinar. Very much looking forward to today's webinar. My name is Tim Ports. I'm the executive editor of Biomass Magazine. I'll be your host for today. The second of what's become an annual tradition here at the Biomass Magazine webinar series, a webinar on best practices in biomass facility dust explosion prevention and protection. A very popular webinar. Obviously, controlling these types of unfortunate occurrences is tantamount at most facilities across the country. Today's speakers will be Dr. Bob Zalosh from Fire Explo. Dr. Zalosh will be followed by Zarko Ognjenovic from the Milton J. Wood Company, and the last presenter this afternoon will be Burke Desitels from IEP Technologies, today's sponsor. A couple of programmatic and logistical notes before we have a look at what we'll be talking about on today's webinar. This is an interactive webinar, meaning that our audience can ask questions. There is a questions button on the dashboard of your GoToWebinar screen. Simply indicate in your question who the question is for, and those questions will be forwarded to those presenters after their presentations have been given. I've made the commitment to the presenters that I won't trouble them with questions while they're presenting, and instead will forward those questions along at the conclusion of their presentations. If the question is a question for everybody that you feel would be worth asking in our question and answer portion at the end of all three presentations, just indicate that by saying all with your question, and I'll be happy to select a handful of the best questions for live responses. If the question is for a particular presenter, I have asked those presenters to stay on the line and answer the questions that are specifically for them via the same portal. So if you ask a question, there's a very good chance you'll get an answer and a response. Certainly, it's a component and a functionality of the GoToWebinar platform that past attendees certainly have enjoyed, and it really does round out the experience. So let's talk a little bit about what we're going to learn on today's webinar as we work through the process. The webinar overview is, we'll start with principles of combustible dust explosions. That'll be the first thing that we tackle. We're also going to talk about primary and secondary explosions. We'll talk then about hazard assessment and ignition risks. We're going to talk about fire protection requirements. We're going to talk about fire protection examples and best practices. We'll talk about explosion protection strategies. And we'll also talk finally about process vessels at risk. The experts are looking forward to covering all of these topics, and we'll start this afternoon's presentation or webinar with Dr. Bob Zalosh. Dr. Bob Zalosh is from Fire Explo, and he'll be talking, as you can see here on the screen, dust explosion hazard analysis for biomass facilities. A great place to today's discussion. Again, you can submit questions using that question portal, and we look forward to the presentations today. Dr. Zalosh, the webinar is now yours.
Okay, thank you, Tim, and hello everybody online. The discussion I'm going to provide of dust explosion hazard analysis for biomass facilities is intended to lead to the determination of appropriate explosion prevention and explosion protection measures. Okay, we're going to begin with the elements of a dust explosion as illustrated in this slide. We start with some combustible powder or dust sitting on a surface inside or outside process equipment. We then subject that combustible powder or dust to a disturbance or airflow so as to lift the dust and form a dust cloud. If the concentration of the dust cloud is greater than the minimum explosible concentration measured for that particular dust, and if the dust cloud encounters an ignition source, the result is flame propagation through the dust cloud, what's formally called a deflagration. If now the deflagration occurs in a confined area, that confinement is all that's needed to produce the dust explosion that we want to prevent or protect. Why and when does a burning dust cloud result in an explosion? The answers are when the dust particles burn rapidly and enough and are sufficiently concentrated for the flame to propagate through the suspended dust cloud, and when the cloud is burning in an enclosure that restrains the expansion of the hot gases produced by the burning dust particles. It is this restraint of the normal expansion that generates the pressures that we associate with a dust explosion. Some examples of biomass facility process equipment where a dust cloud may be present during normal or at least some of the operations are particle size reduction equipment such as a hammer mill, conveying equipment such as a screw or belt conveyor, a pneumatic air transfer duct, and a bucket elevator. Storage bins and silos have dust clouds during the loading of that equipment. Media dust collectors have dust clouds during the pulsing, and those dust clouds can result in the dust collector explosion you see here. Cyclones, pellet coolers, and rotary dryers. I'm now going to start discussing frequent ignition sources in this equipment. In the case of mills and conveyors, a common ignition source is tramp metal brought in with the biomass feedstock in the form of screws, bolts, nails, wire, and other metal that's inadvertently been included with the biomass delivery to the plant. It's possible in many cases to remove that metal by installing a magnet on or over the conveyor or by providing an electromagnetic pulley that will divert the ferrous metal from the normal process flow stream. We're looking at, in this slide, the result of tramp metal being impacted by swinging and rotating hammers in a mill while the biomass is being milled. The impact and frictional heating of the biomass material produced the ignition and char layer that you see on the hammers. The result in this case was a dust explosion in the mill that caused serious burn injuries to the mill operator. Common ignition source in the case of bucket elevators is misaligned belts rubbing against the housing and on the accumulated biomass material. The result is heating of material, heating of the housing, producing these witness rub marks that you see in the top photograph. In the case of conveyors, a very frequent ignition source is an improperly lubricated bearing. The photos at the bottom of the slide show a bearing that's been removed from the discharge conveyor under a canola meal silo. The hot bearing ignited the canola meal in the silo, produced a smoldering fire. The pyrolysis and incomplete combustion gases from that burning canola meal generated flammable vapors at the top of the silo that were subsequently ignited and produced an explosion. The photograph on the left of this slide shows the result of a dust explosion in a bucket elevator and conveyor at the top of some silos at a grain elevator terminal. The explosion propagated to other areas of the plant and equipment in the plant. In the photograph on the right, in the foreground, we're looking at the debris from a fire in a wood pellet plant. The fire was initiated in the conveyor transfer from the pellet storage area to the silo at the rail loading station. In the case of biomass dryers, two common ignition sources are overheated particulate accumulations in the dryer and recycling of fines that have already been dried. So the additional heating can raise the temperature of the fines or the accumulated particles up to the ignition temperature. The photographs on the left show the fire damage to a large rotary drum dryer due to recycling. Fire was initiated by the recycling of fines. In the photograph on the left, we're looking at the discharge end of a large rotary drum dryer at a wood pellet plant. The explosion occurred in the dryer. It blew off the other end, the front end of the dryer, and the blast waves from the dryer explosion blew off the walls in a large portion of the plant. In the case of storage bins and silos, an important ignition source is self-heating of certain biomass material. This self-heating can be initiated by microbiological processes or the condensation of moisture in the silo. Those initial processes raise the temperature of the biomass enough for chemical oxidation to take over, and if allowed to continue for a long enough period of time under warm ambient conditions, can eventually lead to spontaneous ignition and smoldering of the biomass in the silo or bin. The ignition sources that I've been describing in mills, dryers, pelletizers, elevators, and conveyors produce sparks, embers, and burning fines that can be transported downstream to equipment such as coolers, silos, and dust collectors. The simple isometric process flow diagrams that you see on the slide for one version of a pellet mill show examples of the transport to equipment that allow this transfer of ignition sources. They include the inclined belt conveyors, bucket elevators, and screw distribution conveyors that feed the pellet mills. The hot pellets can be transported either by inclined paddle or belt conveyors or bucket elevator to the pellet coolers. And air ducting take the fines to a cyclone. Other conveyors bring it to a silo or to the packaging area. So these are paths for ignition sources to be propagated to the downstream equipment. Photographs we're looking at on this slide show examples of biomass cyclone and silo fires and explosions. In the photograph on the lower left of the slide, we see the result of an explosion in a canola meal silo. The flammable gas and vapors were produced by the pyrolysis and smoldering in the silo. The air needed to form the flammable mixture was introduced by the misguided making of large holes in the wall of the silo in an attempt to reach and retrieve and remove the burning canola meal. In the photograph on the right, we're looking at firefighters trying to extinguish a nasty fire in the large cyclones downstream from a dryer in a wood pellet plant. Dust clouds and ignition sources also occur outside equipment, of course. In the photograph in the upper left, we see a small dust cloud generated at a corn unloading station. The dust cloud is relatively dilute above the grading at the unloading station, but a more concentrated dust cloud exists in the receiving pit, which is a more confined area under the grading. In the photograph in the lower left portion of the slide, we see a more concentrated white powder cloud when a bag of the powder is emptied into an open batch drum along with other material will be used for blending. When you have an open dust cloud outside the equipment of the plant, the National Electrical Code Hazardous Location section dictate that a Class 2 Division 1 and Division 2 area have to be prescribed around that dust cloud source. The diagrams you see in this slide, which came from the NFPA 499 recommended practice, show the extent of the Division 1 area and the annular Division 2 area surrounding the dust cloud. Even if you don't have a visible dust cloud, accumulation of combustible dust on electrical outlets, wiring, and equipment such as motors can be used to designate a Class 2 hazardous location when the depth and amount of that accumulated dust exceeds threshold quantities that, for example, are shown in this at the bottom of this slide and are spelled out in some of the other NFPA standards. This slide shows an example of explosion propagation through interconnected equipment in one biomass plant. The photograph on the left shows the mills in which the explosion was initiated. You can also see evidence of the burning wood in the lower section of the feed duct to the mill. And in the next photograph, you see additional evidence of burning higher up in the feed duct. This feed duct was connected to a long run of horizontal ducting under the ceiling, and that tubing ran all the way to the receiving area of the plant, where unfortunately a front-end loader operator was trying to put some of the received wood particulate on the feed conveyor at the time of the explosion. Unfortunately, he suffered fatal burn injuries in this incident. There was a second casualty located at a baler far downstream of the mill. So this is an example of explosion propagation both upstream and downstream, and demonstrates the need for explosion isolation devices that Burke Hotels will be describing for you later in the webinar. This slide shows another example of explosion propagation through ducting. In this case, the ducting is leading to and from a cyclone on the roof of an animal feed plant. The explosion that occurred in the cyclone propagated back through the inlet and outlet ducting to other process equipment. The ducting in the building also was breached and created a secondary dust explosion due to accumulated dust in the building. Fortunately, in this incident, there were no injuries and only minor damage to the building, but it's another example of the need for explosion isolation devices. in the interconnected ducting. In this slide, we're looking at photographs of buildings at a wood pellet plant that experienced an explosion and fire. In the foreground is a large receiving area at the plant. In the back of that building was some classifying and screening equipment and also a dust collector that had explosion vents, but the explosion vent released and vented towards a group of wood silos that were only a few feet from the wall of the building. The other buildings in the plant housed the dryer, the pelletizers, and the pellet cooler, among other things. In this incident, hot ember generated in the pelletizer traveled to the cooler and ignited fines. Ember and burning dust were transported to the dust collector where the explosion occurred. The collector door and ducting were breached, but the explosion did not propagate back through the inlet ducting because of a explosion isolation device in the duct. The vented flame from the dust collector explosion impinged on the silo outside the collector. The silo fire that resulted required 14 hours of firefighting for extinguishment. Fortunately, there were no injuries in this incident. Another wood pellet plant explosion and fire occurred in this example, where wood dust explosion occurred in the production room, propagated to the storage area and throughout the building. The fire spread through the building and eventually caused roof collapse. One firefighter and one employee were injured during this explosion. When explosions like this occurs, OSHA is going to be at the plant shortly thereafter. In the first incident, OSHA inspected the plant and eventually cited the plant for serious violations of specific OSHA regulations and also for violating the Section 5A1 General Duty Clause, which requires a workplace free from recognized hazard. NFPA standards were offered as examples of recognized hazards and examples of abatement measures. In this case, the plant successfully hired an independent consultant to review proposed abatement measures and satisfy the settlement agreement for the incident. In the second incident, OSHA found that the retention bin at that plant lacked spark detection, explosion suppression, fire and explosion isolation, and explosion venting devices. A conveyor system carrying combustible wood products lacked fire detection and fire suppression devices. OSHA cited the plant for 11 serious violations of workplace safety standards and required corresponding abatement measures. In this case, the plant was eventually shut down. Also, OSHA can conduct inspections without any incident if a plant employee communicates to OSHA that he or she is concerned about unabated fire and explosion hazards due to combustible dust at the plant. And each OSHA area office is also obligated under the Combustible Dust National Emphasis Program to conduct a few random inspections, even though there is no employee complaint or incident. This slide shows the relationship between various National Fire Protection Association standards applicable to biomass facilities. On the left, we start with the newest and most general standard on fundamentals of combustible dust. Depending on the type of facility, there are other applicable standards that need to be followed in addition to 652. In the case of wood pellets, it would be NFPA 664. In the case of agricultural biomass, it would be the NFPA 61 standard on prevention of fires and dust explosion at agricultural processing facilities. These standards also refer to other NFPA standards, such as NFPA 654, which has valuable information on spark and ember detection and extinguishing systems and explosion isolation systems, as well as explosion protection for individual process equipment. Those standards also refer to NFPA 69, which provides the detailed requirements for explosion suppression systems and for explosion isolation systems. The NFPA standards require a dust hazard analysis for all facilities handling, processing, or storing combustible dust. The NFPA 652 standard in particular has specific requirements and a scheduled completion dates for the dust hazard analysis. The 652 standard requires that the dust hazard analysis to evaluate the fire, deflagration, and explosion hazards and provide recommendations for managing those hazards. Where such a hazard exists, the identification and evaluation is required for specific fire and deflagration scenarios. In other words, there's a need to identify where and how the dust clouds are formed or the dust layer is ignited, what the ignition sources would be, what the results of an unmitigated fire or explosion would be. The dust hazard analysis shall also address potential deflagration propagation between parts of the process system and potential deflagration propagation between buildings or building compartments. The DHA shall compare actual or intended dust accumulations to the thresholds for flash fire and for explosions, which are described in the individual standards for the wood processing, agricultural facilities, and for other combustible dust commodities and other similar standards. There's a dust hazard analysis schedule required by 652 for new facilities and for significant modifications of existing facilities. The analysis has to be completed as part of the new facility development project. For existing facilities not undergoing significant modification, the dust hazard analysis has to be completed by September 15th, 2018, 3 years from the effective date of the standard, September 15th, 2015. So plant owners and operators have about 5.5 months to initiate the first dust hazard analysis and have about 2.5 years to complete the dust hazard analysis for all the combustible dust areas in existing plants. Okay, I'm going to conclude my portion of the webinar with a slide illustrating the results of a flammable vapor explosion that occurred at a biodiesel fuel production facility. Just to remind folks that in biofuel plants where there's combustible liquids that are heated, there are flammable vapor explosion protection, in addition to the explosion protection that may be required on the dry side of the plant due to the combustible dust hazards that we're addressing in this webinar. That completes my portion of presentation, so I'm going to throw it back to Tim.
Dr. Zalosh, thank you very much. Great foundation for the remainder of the webinar. Today's webinar is brought to you by IEP Technologies. IEP Technologies, the name to trust for industrial explosion protection. IEP Technologies is the worldwide leading provider of industrial explosion protection systems and services. For over 60 years, we have provided protection solutions that can suppress, isolate, and vent combustible dust or vapor explosions in process industries. IEP Technologies can support biomass and ethanol operations through our facilities in the United States, Brazil, the United Kingdom, Germany, Switzerland, France, Turkey, and China, designing and servicing systems with a dedicated team of application engineers, regional sales managers, and field engineers. The IEP Technologies process, precise protection for every application. IEP Technologies has more worldwide experience protecting a wider range of facilities against explosion than any other company. With well over 15,000 systems installed, we have developed a unique process to ensure the highest level of protection for your facility. The IEP Technologies process includes material testing and engineering site visits, system design, installation, commissioning, and maintenance. IEP Technologies also offers on-site training programs for the proper operation and understanding of your explosion protection system. IEP Technologies is a member of the Herbiger Safety Solutions business segment, which provides comprehensive industrial safety solutions across a wide range of industries. Saving lives through explosion protection and prevention is the role of IEP Technologies, Gale, and Brillex brands at Herbiger. IEP Technologies is the systems and service specialist for the entire range of explosion protection solutions in dust and gas applications. Gale brings decades of experience in mitigating fire and explosion risks from electrostatic spark discharges. Brillex contributes its technology leadership in advanced venting systems. These brands complement the flameless venting expertise that Herbiger has accumulated over the decades. You cannot afford to let an explosion threaten your critical facility. Let us work with you to keep an explosion from impacting your bottom line. Call IEP Technologies today. Back to our webinar. Our next presenter this afternoon is Žarko Ognjenović. Žarko is going to talk about fire protection in a biomass facility. Žarko is from the Milton J. Wood Fire Protection Company, and we look forward to his presentation. Žarko, go ahead.
All right. Well, thanks, Tim, and good afternoon, all. I really appreciate the opportunity to present you with this very brief outline of the process behind designing, constructing, and operating the key fire protection and explosion prevention features in a biomass facility. So the presentation goals this afternoon will be to identify the process of defining which fire protection and explosion prevention systems are mandatory and which ones are optional when constructing a facility, to identify the process of designing and installing those systems, and to give you a few best practice examples. So to start with, let's see if this works. So how do we design and operate a biomass facility? First starting point are the building and fire codes. They tell us what we must do. They're basically the law of the land, so they're clearly mandatory. And they're almost exclusively occupancy-based, based on the buildings or occupancies that house the equipment. The next building block are the adopted standards. They tell us how to do it. Those standards that are referenced in the building and fire codes are mandatory. Some, like insurance standards that might go above and beyond the mandatory standards, could be optional, and that depends on the relationship you have with your insurer. Few of the standards remain occupancy-based, but there's a clear shift into targeting a specific process or a system with these adopted standards. And so we arrive to the next key building block, which is our process hazard analysis. This is strictly process and equipment-driven evaluation that has a mandatory implementation aspect and an optional implementation aspect. An example of the mandatory implementation aspect is the PHA itself. it is mandatory for all facilities that handle hazardous materials like combustible dust. Furthermore, if we have an explosion hazard that's identified within the PHA, the protection option must be implemented. It's not an optional. The optional implementation aspect, or an example of that, would be if a fire hazard is identified inside of the process. One could elect to disregard the equipment-specific protection and rely on the building sprinkler system or a manual firefighting through standpipes and hoses, rather than installing an automatic fire protection system inside of that equipment. As a result, they might lose this piece of equipment, but if it's easily replaceable, if there's no danger to human life during the event, that might be just okay with them. It comes down to how much risk tolerance does an organization have. And last one is our government regulations. That would be an OSHA, EPA, and similar, that are clearly leaning more on the operational rather than an upfront design and construction side of things. So in the interest of time, the PHA and the government regulations are not going to be subject of this presentation. So with this click of the button, I'm going to make them disappear from the slides, and on we go with our building and fire codes. So what are they? As I mentioned before, they're adopted and written into the laws on a state-by-state level. The most widely used in the U.S. are the International Building Code, International Fire Code, and NFPA. There are some other fire and building codes that are implemented in other states, but these would be most dominantly used. They tell us what to do, and they tell us what to do both for any type of occupancy and then specific to the occupancy type. So they also tell us where to look for on how to do whatever they ask us to do, and that's through their reference to design and installation standards. So what's defined in the building and fire codes? Many things on the construction side, on a fire protection and explosion prevention specific side. We have a fire service features, we have emergency planning and preparedness, fire resistance rated construction, fire and smoke protection features, fire protection systems, control of ignition sources, means of egress, housekeeping and maintenance, and some others. So an example that's very often overlooked in the initial design stages of the facility are the fire service features. So all facilities, irrespective of their function, must be provided with full access into and around the facility by the responding fire brigade, and with an adequate water supply to fight fires expected in the facility. So as far as the full access is concerned, typically 20-foot wide road within 150 feet of any exterior wall in the facility. Water supply, volume, and duration, they're based on the larger of the two things. One is the total surface area or square footage and construction type of your largest building in a facility. And two is the most demanding automatic fire protection system demand. So whichever one of these is larger, that's what you need to size your water supply to. Apart from those general requirements, the code defines the occupancy-specific features based on use and occupancy classifications. So, and typically the operating structures in a biomass facility will fall into one of the following classifications. We have an F1, factory occupancy. We have an S1, or storage occupancy. We have an H2, a high hazard occupancy containing materials that pose a deflagration hazard, as is the case with our combustible dust. And we have an H3, high hazard occupancy, that contains materials that readily support combustion. And that example is combustible fibers. Our slide here is messed up a little, but so excuse me for that. So the question asked is, does any flammable or combustible liquid, combustible dust, and combustible fire inside of an occupancy automatically qualify it as H2 or H3 occupancy? And the answer is clearly no. Only when we exceed the minimums allowed by the building code in case of the flammable and combustible liquids and combustible fibers, and that's the table 307. I'm just going to give you a snapshot of that table. if the presentation cooperates with me. And this table basically gives you the maximum allowable quantities in a control area in your facility, either stored, used in a closed process system, or used in an open process system. And if you exceed these quantities, you will no longer be able to qualify the facility or the occupancy as F1 or S1. You'll have to go to H3 in this case, or H2. In case of the dust, combustible dust, if you exceed the quantities that are the minimums that are prescribed by NFPA standards, 654, 664, 652 that Dr. Zalosh just mentioned, then you would fall into an H2 occupancy category. So, crucially important for the occupancies that are originally designed, permitted, and constructed as F1 and S1, as most of our biomass facilities are, they must be operated in a way that will not move them into H2 or H3 occupancy. And how do we do that? Very simply, it's housekeeping. We need to keep the hazardous materials below the minimums allowed. Material control and housekeeping. So what all is determined based on the occupancy classification? Type of construction, construction methods and materials, maximum area and height of our buildings based on them being or not being protected with fire protection systems, structural requirements, EMP, electrical, mechanical, plumbing requirements, fire and smoke management, means of egress, and fire protection requirements. So fire protection requirements specific to this presentation contained in Chapter 9 of Building and Fire Codes. And automatic sprinkler systems are one of the top ones in line for that. They are mandatory in all F1 occupancies over 12,000 square feet. Furthermore, they're mandatory in all woodworking F1 occupancies that generate finely divided combustibles that are over 2,500 square feet. They are mandatory in all storage S1 occupancies over 12,000 square feet. And they are mandatory in all H2 and H3 occupancies, irrespective of the square footage of the building. The code allows for use of alternative automatic fire extinguishing systems. And I know we have probably a lot of people here from the pellet industry and other biomass industries that are not particularly fond of water. There is an option in the codes for those buildings that they do not wish to protect with water to protect them with an alternative system. The picture on the right hand of the presentation shows the gaseous suppression system. There are some other options with dry chemical systems and some other systems, but they are allowed by the building code only if accepted by the code officials as an alternate to the sprinkler systems that are mandated in Chapter 903. Fire Protection Chapter 9 further describes the requirements for the fire detection alarm systems, typically based on a number of occupants in the building. Our standpipe systems, typically based on the height of the highest operating floor above the road, or the depth of the basement operating floor above the or below the operating roadways that are used for fire department access. Typically anything that's over 30 feet in height requires a standpipe. Then we have fire extinguishers, pretty much common these days and located throughout the facilities. We have our smoke control systems, smoke and heat vents. Again, very often disregarded in the initial design stages. Clearly required by the building code for any F1 and S1 occupancy that has more than 50,000 square feet in undivided area. And lastly, for this slide, we have explosion control. So where we have a structure, room, or a space that's occupied for purposes involving explosion hazards as identified in this table, and you can look at the excerpts from the table in the bottom left corner. Combustible dust is one of them, and our explosion venting or explosion prevention systems are required. Again, this is occupancy-based building code. We are talking about explosion venting or explosion prevention systems for the rooms or spaces within the structure, not specifically equipment. So building and fire codes further expand into the specific types of facilities. Couple of examples I'll give you here are from Fire Code Chapter 13, combustible dust producing operations. You can find the requirements for those in Chapter 13, and we also have Chapter 19 for the lumber yards and woodworking facilities that clearly apply again for our biomass manufacturing facilities. As far as the adopted standards are concerned, they are one of three kinds. Those specifically called for in the building and fire codes. They would be referenced NFPA standards typically in the U.S. Those that are specifically adopted by the states across the board. And an example of that would be in the state of Florida. There's a list of NFPA standards that are, again, adopted across the board and are mandatory to be used, irrespective of the fact that they might not be specifically called for in a building code or a fire code. Then we have the insurance underwriter standards. Again, often overlooked initially in the design stages of the facility, very costly to implement later, and FM Global data sheets are most commonly used for HPR or highly protected facilities. And again, adopted standards tell us how to design, construct, and commission the systems that are required by building and fire codes. Examples of the adopted standards would be in Chapter 13 that I mentioned before for the combustible dust producing operations. If you are one of those, they will be Table 1304.1 that will specifically call for you to comply with NFPA 69, explosion prevention, NFPA 654, manufacturing, processing, and handling of combustible particulate solids, NFPA 664, prevention of fires and explosions in wood processing and woodworking facilities. What's defined in adopted standards? They give us the details on how to design, install, commission, and maintain the systems that are required by the building and fire codes. The emphasis is on life safety, either through the active systems or passive building and process features. Our insurance company standards, in addition to life safety, they emphasize the protection of property and business interruption concerns. So just by this definition, they would by nature be more strict and more demanding. I'll give you a few examples of the best practices from some of the biomass facilities. We have our dust collectors or air filters. The example on the right-hand side is for the dust collectors located outside. The one on the left is one located inside. Typically, you're going to see explosion vents. These are explosion vents on the outside air filter or dust collector. This is actually an example of a badly placed explosion vent because the explosion isolation device that you see on the return duct is located directly in the path of the blast zone. Better example of that is on the left-hand side, and that is our flameless vent example on the dust collectors located inside of the facility. If explosion vents are not on your menu, either you have no ability to put them in, or you cannot. You're prohibited from putting them in because of the nature of the product that you're handling inside of your dust collector. Explosion suppression is definitely a viable option, widely used for those purposes. We also have isolation from connecting processes. Dr. Zalosh, his presentation showed some of the examples of what happens if you don't have these systems in place. The example or the picture on the left-hand side shows the explosion isolation device or back pressure valve. On the right-hand side, we have a chemical isolation, which is injecting suppressant, in this case, in duct. We also have spark detection and extinguishing systems. Those are typically put on the ducting that leads into the air material separators or dust collector. And you can see on the left-hand side, there's spark detector, spark or ember detector, that's looking for the qualifying particle, ignition source, before it gets into an enclosure that's obviously full with fuel. And then it extinguishes it further downstream before we enter into the enclosure. And you also have dilute systems. These are water-based systems, and you can see an example on, in this case, of the dilute system that has nozzles on the dirty side of the dust collectors. I see many times dust collectors that have nozzles on top in the clean space. Pretty much useless there because there's no way for the water to make it down to the, effectively make it down to the fuel which is located on the dirty side. Mills, we have plenty of those around. We want to see the explosion events, or we might be mandated to put explosion events on our intake bins, depending on the material type. If we have coarse material like wood chips, we might not have to do that. If we have fine material like sawdust or fines, we more likely will have to do it. We put explosion vents or discharge plenums from the mills. We want to also put the dilute systems in a discharge plenum. So clearly the plenums are full of fire load material, and if there is an ignition of that material inside of the plenum, this is the way to extinguish the fire. Further on mills, mechanical or chemical isolation from connecting processes, typically rotary valves, upstream of the mill, screw conveyors, downstream or on the outtake of our material from the plenum. Then we have either the explosion isolation device or a chemical isolation on an air duct leading into our air materials separator. Then we also like to see the spark detection extinguishing at our mill discharge. Here's an example of the detector that's looking at what's coming from, in this case, a pellet mill. A malfunction in a pellet mill can create an amber that can fall down through the chute. The detector will see that amber, and it'll extinguish, the system is going to extinguish it before it gets either in the conveying system or in some type of a pellet cooler in this case. Silos, plenty of those around. Again, explosion vents, depending on the material type, are a must. Mechanical or chemical isolation from connecting processes, rotary valves or screw conveyors up on top, as well as on the outtake. Chemical isolation on ducted aeration system that might be leading to a different kind of a process or something along those lines. We also have an option to put spark detection extinguishing at a silo intake to screen the sensitive material or potentially hazardous material that comes into the silo. This picture shows the manually operated dilute system at a silo roof. So we have two options there. One is applying water to the material that's inside of the silo. The other one is actually applying water and spraying up on the roof structure and sides of the silo. Very often, after years of use or months of use, sometimes there are heavy deposits of the either dust or chemical residue in the silo structure that, if ignited, can cause a substantial hazard and structurally impact the silo. We also like to see the dilute system in the silo chute. Those systems would be used if we have to evacuate the product that has a hotspot inside of it. If the choice of the owner or the operator is to evacuate the product and then extinguish the hotspot as it exits the silo, if it can be detected effectively, exit the silo before it gets exposed to the oxygen in the air and results in a flashover, dilute system is the system of choice there. We also have a gaseous inerting system that we can put in a silo. A couple of flavors there. We can go and admit the liquid suppressant into the top of the silo. As it hits the air inside of the silo, it's going to vaporize and apply the suppressant into the top portion of the silo. We can also inject the vaporized suppressant either through some type of aeration system that might be present in the silo or through the sides of the silo into the product mass, let it percolate through the mass, which takes a lot of time, and then let it reach the concentration that is adequate for effective fire suppression. And lastly, we have some few examples from the rotary dryers. We have a dilute system at a cyclone top, explosion vents at cyclones, not unlike our silos or dust collectors, spark detection and extinguishing at a dryer drum discharge, and sometimes at a cyclone recirc duct discharge, sometimes also on the material outtake from the cyclone as it leaves the drying system. And then we have the furnace and dryer inlet misting systems that are typically used for process control that can be used for fire protection if needed. So with all these options, how does one know what to provide? Basically, there are three things. One is what's mandated in the codes and standards, what's identified as required in the process hazard analysis, and what's required by one's insurer. That's all you have to do. And last slide, we have first and foremost to design facility per codes, standards, and PHA. We have to operate it as designed, and we have to manage the changes in a facility just like we did it when we initially designed it. So any change in the facility, we have to design per codes and standards and PHA. And that's all I have for you this afternoon. I appreciate the opportunity to provide you with this presentation.
Žarko, thank you very much for that very informative presentation. I really am enjoying this webinar, and I know that these are really critical operational concerns that, again, by the virtue of the industry that we're in, dust is a reality of our production environments, and the safe management of that is paramount. Really is a top consideration of most of the plant managers that I talk to. I know that this is certainly top of mind, keeping their employees safe first, and then of course maintaining their asset and making sure that they're protecting that as well. So our last presenter this afternoon is Burke Desitels. Burke is the Vice President Aftermarket at IEP Technologies, and certainly looking forward to his remarks. Burke, go ahead. Looking forward to your presentation.
Great. Thank you, Tim. Just to let everybody know, my role in the aftermarket business is after the systems have been sold, I'm responsible to manage the designs of the systems, the application engineers, and the proper installation and commissioning of the systems with our group to make sure that when these systems get called into action, they work properly. So as we discussed earlier, Bob did a great job and Žarko followed up. Here are the most prevalent pieces of process equipment in the biomass industry that we come across that have that high combustible dust fuel mixture, and also has the potential of the ignition source that can lead to the explosion. And the explosion can be protected by these main protection techniques: containment, inerting, venting, suppression, and isolation. Containment, real quick, is simply designing the vessel real strong so that when the combustion event occurs, the rupture from the deflagration event does not occur. So it's designed real strong to withstand the pressures. Inerting is very simply you displace the oxygen with a non-combustible, non-oxidizing material such as nitrogen or CO2 so that the combustion triangle can never occur. These two types of techniques, although they're code recognized and absolutely fine protection techniques, they tend to be too expensive in the types of applications that are associated with the biomass industry. So typically, suppression and isolation are the most common techniques that are utilized in the industry. Before you can size venting, suppression, or isolation, you need to understand the combustible characteristics of the dust itself. So you need to know what KST and Pmax are. These are the explosibility characteristics of the dust itself. So what you're seeing here is a picture of a 20-liter Kuna sphere, and this is the industry agreed upon size vessel for combustible dust. And the way KST and Pmax are determined is basically you take a sample of a sieve material, put it inside the vessel, and you ignite it. And you record pressure over time. And the KST is simply the maximum rate of rise, the dPdt of the combustible dust itself, times the cube root of the vessel that it's tested in. So as you can see, the 20-liter sphere, the volume of the vessel that it's tested in is critical. 15, 20, 25 years ago, there were a lot of tests that were based upon a 1-liter Hartmann tube, and they would produce lower results than what a 20-liter sphere would produce. So if you do have an old test report, please review it, confirm that the material has been tested, and it's to the current standards, ASTM E1226. A lot of misnomers out there about KST I come across. People let me know that the material isn't that explosive because the KST isn't that high. It's only 50 or 60. Really, that just tells you you have a little bit longer time to deal with the explosion and put it out. However, it's still going to be under a second. What you really also need to keep your eye on is Pmax. So that's the maximum amount of pressure that a combustible dust explosion will produce. And typical values of Pmax are from 6 to 10 bar, which is about 90 to 150 psi. So even though your KST may be quote-unquote relatively low, you still have a very combustible and rapidly producing pressure explosion hazard that can happen inside your process. And this industry, NFPA, have agreed upon ST1, 2, and 3 designations for combustible dust. And almost all of the biomass hazards, whether they be agricultural or wood, cellulose-based materials, are typically going to be ST1 dust. You're going to have KSTs, from 70 up to 150, and then some of the finer materials might be around 180, and then they may possibly go over 200. But for the most part, they're going to be ST1 dust. Now, the first main protection technique that's utilized in explosion protection is venting. And that's simply a weak membrane on the sidewall of the vessel that opens up at a predetermined set point. So based upon the strength of the vessel, the size of the vessel, the combustibility of the material, NFPA 68 determines what size and amount of vent area is required to provide proper protection. Explosion vent panels can come in various sizes, shapes. They can be rectangular, they can be round, they can be flat, and they can be domed. It's all based upon the application. The flat rectangular domes are more cost-effective and easier to manufacture. However, they have limited vacuum resistance, limited cycling applications. So depending upon the process pressure conditions, that will drive what type of vent panel makes the most sense for a given application. Here's a picture of a vented explosion, and as you can see, the fireball grows quite big. The fireball itself, the hot expanding gases, it's going to follow the ideal gas law, and it can grow up to 8 times the size of the volume that it originates in. And you can get flame ejections that can be quite large. So you need to make sure, if you're using an explosion vent panel, that you have a safe area to vent that fireball to. Here's a quick video clip of a vented explosion between 2 vessels. This was done over in Germany. All right. Let's see if I can try it again. Okay, as you can see, you get a pretty significant flame ejection. This is just put in place here to illustrate that, that definition of a safe area really needs to be considered to make sure that venting is the proper solution for a given application. Here's that pressure time curve that we saw earlier, except you can see the effects of putting an explosion vent panel on the vessel itself. So here is the curve of the unvented combustible dust explosion, and you can see here's where the opening of the vent panel occurs, and here's the resultant or reduced pressure that the vessel needs to withstand, and as you can see, the P red is below the strength of the vessel, so it provides proper protection. NFPA 68, you need to know what the strength of the vessel is. That's a key ingredient in sizing these systems. But you need to keep in mind that venting will not do anything to stop the flame propagation. So there may be subsequent fires or whatnot with the material after the event, and that you can't vent inside the process equipment. You can use vent ducts to take the vent and the fireball to outside the building. However, there's going to be a penalty in the NFPA calculation when you do that. The slug of air that is in between the vessel vent membrane and the sidewall that goes outside the building, that air needs to be pushed out of the way by the fireball. That's going to create a back pressure, resulting in the need for more vent area. There is the possibility of using flameless vents. Flameless vents work by having the flame pass through a mesh membrane, extracting the heat and keeping the flame from propagating outside the vessel. Keep in mind that you're not going to get the full vent area when you use a flameless vent. You're going to have an effective vent area which is a lot smaller than the actual opening itself. And you do need to make sure that there's a safe zone around the flameless vent because hot gases are still going to propagate outside of the flameless vent itself. As you can see here is our spring-loaded type explosion vent panel. There's a plate on the sidewall of the vessel held back by a spring. And when the pressure wave and fireball hit the membrane, it pushes up on the spring, allowing the flame to propagate through the mesh membrane. As Bob illustrated earlier in the presentation, there's a need for proper isolation in between connected vessels. As the fireball starts to propagate, it can very easily propagate upstream and downstream from the explosion hazard as long as there's fuel and air inside the interconnected ducting. So NFPA recognizes the need for isolation between devices. The isolation types can be active. It could be a chemical isolation where it discharges copious amounts of agent into the ducting to provide an inert barrier and extinguishing zone to stop the flame front. Or it can be an active mechanical device such as the knife gate shown in the picture on the right, where the nitrogen bottle drives the piston down and provides a mechanical barrier from the flame front. There are also passive isolation systems, isolation valves that are available. The flap valve opens up with the airflow from the inlet to the dust collector, and when the pressure wave and fireball hit the gate, it closes it in place, providing that mechanical barrier. The pressure wave is always in front of the flame front, and that's what allows these types of devices to work. Last main type of protection system is an active suppression system. This is a system that consists of a pressure detector that detects the explosion during the early stages, a control panel that monitors and activates the extinguishers, and they discharge agent directly into the process to extinguish and suppress the event before the pressures reach destructive levels. Three main components, as I mentioned. There's the actual pressure detectors that sense the explosion, the control panel that monitors and activates the bottles, and also provides the process shutdown to interlock and make sure that the flame doesn't propagate to any parts of the process after the suppression occurs. Pressure detection is probably the most important part of the suppression system. You need to have reliable detection of the event, and you need to detect the pressure event reliably before it gets too far. The main type of detector that we use is electronic MEX detector, we call it. It has two capacitive discharge strain gauges that continually sample off the process. It plots a curve and waits for a curve that's associated with an explosion to activate the system. The control panel is essentially a black box. 120 volts gets wired into the control panel. We wire out to the detectors. We have wires out to the bottles. When the signal from the detector is denoted by the control panel, it sends a voltage out to the bottles that activates the extinguishers. There's also interconnected relays that will shut down the process and provide enunciation. The extinguishers themselves are pressure vessels filled with sodium bicarbonate, baking soda, special blend that we use, and it's captured by a burst disc. When the signal comes from the control panel, the burst disc fails. The 900 psi nitrogen drives all the agent out of the bottle through a spreader mechanism to get dispersion into the process, and it provides the suppression. In addition to the KST and Pmax, understanding the process conditions, what is the minimum and maximum temperature of the application, what is the minimum and maximum pressures that the system operates at. These are all ingredients that go into determining what type of detection extinguishers and spreaders are used for the application. Also, knowing the vessel strength and the vessel volume will determine how much agent is required for a given application. All of these different characteristics are imported into our suppression model. It's a third-party approved model for KSTs up to 500. And again, here's that KST Pmax curve that unsuppressed explosion would produce. And here's where we deliver our agent and determine what the resultant reduced pressure for a suppressed explosion will be. So here's a pressure time curve of what occurs for an explosion that's going to be suppressed inside a dust collector. Here are the different factors that go into our decision making on which protection technique makes the most sense. Most of the early questions are determining whether or not venting is a viable option. Venting is a very cost-effective passive solution for explosion protection, and most customers try to utilize that technique where appropriate. But sometimes that's not always a viable option because of that safe area for venting. The next consideration goes into what are the duct configurations. Can passive products be utilized on that? The exhaust duct is a key ingredient. Whether the air is being brought back into the building or exhausted outside will drive what decisions are being made on which isolation devices are utilized. And then you also have to take into consideration the operating pressure and temperature of the process to make sure that you're selecting the right components. Often in biomass applications, we come across a lot of inline fans. Inline fans are considered ignition devices, so the dirty air with the fuel and the oxygen is being passed through the air. NFPA requires that NFPA 69 isolation devices be utilized around the inline fan, whether that's incorporated into the protection system of another device. It depends on the layout of the plant. Lastly, I'm going to talk about the different pieces of process equipment that we come across and what some of the considerations are. We protect more dust collectors than any other piece of process equipment, and it makes sense when you think about it. The finest particles, the driest particles, the most susceptible particles to an ignition are in the baghouse and the air material separators. So there are a fair amount of applications where we protect in baghouses. Now, there are many different types of baghouses, whether they're hanging bag, cartridge types, lower tube sheets, or whether or not they're product receivers, meaning that they're going to have a dense material flow on the infeed, as well as the possibility of house vacuum systems. All these different types of collectors have different requirements for locating equipment. Locate our detectors outside of the media range so we can get a clear detection path to the combustible dust cloud, and we also need to distribute our agent evenly throughout the entire hazard. So depending upon what type of dust collector or baghouse is, will drive the location of the different types of equipment. So here's a short video clip of a mill with a downstream dust collector, and the ignition is going to occur inside the dust collector. The dust collector is protected with an explosion vent panel, and the inlet duct has a passive isolation valve, a flap valve that provides the mechanical barrier. And then the last step is the interlocks to make sure that material is not allowed to continue to move throughout the process where burning embers may allow for reignition. Next type of air material separator we come across is cyclones. It's where material is fed into a cyclonic vortex. The heavy materials fall down and the fines move downstream. With cyclones, there are some different considerations. Typically, you have some high velocities at the inlets for these ducts, and the cyclonic effects on the inlets will create a high wear pattern. So that needs to be avoided with your protection equipment, whether it be vents and or suppression equipment. You want to provide flush-mounted equipment onto the cyclone to make sure you don't destroy the efficiency of the vessel itself. And sometimes cyclones, especially in biomass applications, can be quite large, and it could have an array of 2, 4, 6 cyclones, which have common inlet headers and ducting. And these can lead to extremely large ducts from an isolation standpoint. Mills, pulverizers, size reduction equipment, very common in the biomass industry. Here's that same video clip, except we're going to see the ignition occurring inside the mill and detect it on the discharge. So on the discharge of the mill, there's an optical detector, an IR detector, that senses the flame once it hits the discharge duct, and then the extinguishers associated with that zone of protection discharge to provide suppression and isolation. And again, the control panel interlocked to stop the process equipment. There are many types of mills. Typically, we see a lot of hammer mills, but there could be jet mills, pin mills, vertical mills. Mills typically are of high strength. However, they tend to be the ignition source. They're the high energy point where either tramp metal or metal to metal type of ignitions can occur. Depending upon the type of mill, it might be a direct discharge or it might have a large hopper. And these all come into play on what types of detection and suppression and isolation are utilized. There's also consideration on how air intake is brought into the mill itself. Air intakes are critical for material moving and cooling. So you need to take that in consideration to make sure there isn't a potential for a flash inside the operating room where people may be present. Product conveying, we talked about these. These are typically considered isolation systems, especially with pneumatic conveying. The detection would occur at the vessel's endpoints, and then isolation would occur along the duct itself. In the case for mechanical conveying, if there are transfer points where there may be gearboxes and bearings, they may require additional detection and isolation points. Bucket elevators are a method of conveying vertically, where the material is picked up at the bottom of the bucket elevator and transported to a higher elevation and then dropped off into a storage, typically into a storage silo. And there's a lot of ignition potentials associated with a bucket elevator, as Bob talked about. So the head and the boot are the prevalent locations for the ignition of the deflagration, and then you need to isolate, keep the flame from propagating through the different casings, the infeeds, and dust extraction lines. Lastly, storage silos, very large vessels that the material is stored, conveyed to, and stored. As you can see, isolation can be very challenging to locate on large silos. As you can see here, this is a large pellet silo with explosion venting at the top of the silo itself and isolation on the infeeds. The considerations with a silo are that the protection needs to take into account any sort of fill level that may occur inside the silo. So understanding where the high level and low level indicating switches are located are very important. How the material is fed into the silo, whether it's a single direct in-feed line or it's part of a large conveyor with multiple in-feeds to different silos, all come into play. Lastly, the consideration of how does the silo breathe itself. Material is being moved and displaced inside a vessel, the air inside the vessel needs to be displaced. Is that done through a bin filter, dust extraction lines? Those are vessels or interconnected ductings that would require some sort of protection. So that's the presentation on the different types of explosion hazards, the process equipment and the protection techniques that can be offered. And here's a last consideration list of the different factors that go into the overall protection of a given hazard. Any questions at this point?
Burke, thank you. I'll take over from here. We do have some questions queued up. And I'm excited because we got some good stuff. I'm going to start with a kind of a basic one that, I'll just throw this one out there to the group. And this is from a James Gaffney, and he asked a question: how common are dust explosions at biomass facilities? And maybe sharpen that question up a little bit. Do we have any indication in terms of number of incidents per operating hours? Any bearing that you can all sort of give us on that question from James would be appreciated. And anyone from the group that wants to take it.
I guess this is Burke. Burke Desatel. I guess that's a challenging question to answer, because with any explosion hazard, you have an application that has combustible dust and oxygen in the right concentration, and you're waiting for that ignition source. Now, to statistically pinpoint what is the likelihood of an ignition occurring is not an exact science by any means. However, I will say that we do have hundreds of applications and biomass applications, and we know of successful suppressions that we hear about every year. And I've also investigated, as well as Bob Zalosh has investigated, other explosions that have happened that we've been called in to investigate and provide protection. So it's not something I think that we can qualify or quantify, but we can certainly say that it does occur. Bob, would you like to add to that?
Yeah, thank you, Burke. I'll add a little bit. I also have not seen any hard data on frequency of explosions, but I can say that it's becoming more common to over the web to hear accounts of explosion incidents, that is when the explosion protection or prevention did not work. And there are organizations, for example, opponents to wood pellet plants that put on very active in putting up incident data to make their case. And so I have seen compilations of numerous explosion incidents that just were obtained from data over the web. The individual insurance companies, of course, have more detailed loss data, but even they don't have frequency data to tell you exactly how many hundreds of thousands of hours to expect as mean times between explosions.
Right. If I could just add one other thing. Wood pellet plants in particular, and this is just a general statement, they do seem to have a lot more, a higher prevalence of explosions than other industries that we work in. And I believe it's because, one, cellulose wood has one of the lowest MIEs, minimum ignition energies, of the materials that we deal with. A typical MIE for wood is under 25 millijoules, and 25 millijoules is the benchmark for electrostatic discharge. So cellulose is susceptible to all of the different types of ignition sources. And if you look at a pellet plant, you're going to have hammer mills, conveyors, possibly bucket elevators, coolers, and you're going to have dryers. You're going to have a lot of process equipment that inherently have ignition sources built into them. So I've seen a lot of applications where that dust cloud is met by the ignition source within the pellet plant industry.
Great answers, everybody. Thanks, Bert, for that. I want to remind everybody that next week we are hosting the International Biomass Conference and Expo, and professionals from IEP would be more than happy to welcome all of you at their booth, booths number 1221 and 1223. And that, again, is next week in Charlotte. If you're going to be at that event and you've got follow-up questions for Burke or his team, certainly we welcome you to come to that. We'll come to their booth at the International Biomass Conference and Expo. Burke, you led into my next question just perfectly. There's a question from a Jens Holm from Dong Energy. And the question is this: question concerning the storage of wood pellets in large silos. What protection equipment should be installed to prevent an explosion in the headspace of the silo to propagate, to eliminate the propagation through the silo inlet at the top and further on through the conveyor systems?
Yep, absolutely. Large silos are typically protected. The vessel itself is usually protected by venting, because the amount of extinguishers required to suppress a very large volume can be very expensive very quickly. So most large vessels are protected by venting. The silos are typically outside. They're tall enough that you can locate the vents, that you can have a very safe area. Now your next challenge is where is that infeed coming from? Because given a certain KST, Pmax of a combustible dust, you have a certain size duct, you need X amount of spacing to provide that proper barrier. Chemical isolation tends to be the easiest way to provide isolation on the infeed to a silo. But you're going to need a fair amount of space, and it all depends upon the volume that you're protecting. But a typical inlet could be 3 to 5 to possibly 10 meters away, depending upon how big the vessel is. You want to discharge the agent far enough away from the hazard so you have plenty of time to establish the barrier. However, you don't want to be so far away that you allow the deflagration to pressure pile and transition to a detonation event, which could possibly render the chemical isolation barrier ineffective. So there is a very discrete barrier, min and max distance, that needs to be adhered to. So depending upon the application, we may have to contribute the detection methodology, the pressure detection methodology, by adding an optical detector or an IR detector. So now the pressure detection with the flame sensor is a lot faster and can cover a high amount of applications, which would shorten the distance needed for that isolation barrier. So that's on the infeed itself. Now on the discharge would typically be down at the bottom. There may be either a screw conveyor, or hopefully there's an NFPA approved rotary valve. But what happens in a lot of these cases is that the rotary valve is so big, it's hard to get manufacturing within the tight tolerances for the gaps that are required per NFPA 69. So a lot of times you can't rely upon the rotary valve to be the isolation barrier. So then a separate isolation system would be installed on the discharge. Now on the discharge, you tend to have either, as I mentioned, either screw conveyors or drag conveyors or pneumatic conveying. We're typically at ground level, so then the spacing and access to the extinguishers doesn't become as challenging as it is on the infeed. Great answer. I've got, and I think you're probably going to have a lot of traffic at your booth on next Monday night starting. So I'm happy about that. Some really good questions coming in. We are up against our 3:30 stop. I'm gonna indulge the audience and extend our time just a little bit and ask 2 more questions. I think they're very good. And I'll start with this one from Dirk de Jong. Dirk asks, and I think I'm framing the question up accurately, is there a percentage cost for protection that I can work with alongside or relative to the CapEx cost for equipment and machinery in a wood pellet plant? So
I think what Dirk's asking is what percentage of the overall expense at a wood pellet production facility, new build, should they imagine a really robust fire protection and dust system might cost in a percentage sort of situation?
I can potentially chime in a little bit on that from our experience in participating. This is ARCA, participating in 4 or 5 pellet manufacturing and export facilities. Our experience is that a robust system, a fire protection and explosion suppression system would probably run you in about 5% range of the total capex. Of course, it depends on many, many things, but I would say that's based on the information I have, roughly the number.
Sounds good. Anybody else want to add to that?
Yeah, if I could, this is Burke again. Working with someone like Zarko or Bob on the front end certainly can impact that on the positive end for the end user from an economic standpoint. A lot of times when I get called into action for particular solutions that are being looked at, the plant's already built, they've been running along, either an inspection occurred by a fire marshal or a OSHA inspector, or there's been a combustion event. So I have to protect what I see in front of me. And typically extinguishers tend to be the easiest way to retrofit existing systems. But if you're working with a skilled consultant on the front end, decisions can be made to utilize, venting, passive isolation devices. You can make some smart decisions up in the front end that may be able to mitigate that cost that, again, someone like myself down the stream, I'm dealing with what I see in front of me.
Good. This is Bob. I just want to give a couple of examples of that. Apropos to the previous question, I wanted to add to what Burke was talking about in terms of explosion protection, that prevention measures would include in the silo, case of the silo, and flammable gases accumulating at the top of the silos might include gas sensors such as carbon monoxide sensors to help detect that, as well as some thermal sensors. In the case of decisions on the costs for explosion isolation devices in a plant that has just miles of interconnected equipment, there are ways to estimate the probability of explosion propagation between different sections of equipment, depending on the length and the diameter of the piping or conveyor ducting, and also on the KST of the material. So there are ways to estimate probabilities and therefore make informed decisions on whether you need explosion isolation on particularly small lines that might be on the order of 4 inches or diameter or so, and that again depends on the length of the line, KST, the material. But you can make informed decisions on how much explosion isolation you need using those approaches.
Great answers, everybody. I've got one last one, and then our audience is moving on to other things. So I think this one will be a relatively short one, and I had a couple of questions that came in that are in this ballpark. So I think I'll ask this one, and I think a number of folks will be happy that we asked it. Before I ask the question, I just once again want to thank IEP Technologies for sponsoring today's webinar. Like last year's, I thought this year's was loaded with excellent content, and I know that folks are going to really find it very, very useful. Again, IEP will be at booth number 1221 and 1223 in North Carolina next week for the International Biomass Conference. If you haven't signed up yet and it makes sense for you to be there, certainly want to ask you to join us at that event. The last question is this. This is from John Kriegshauser. John asks, and again, there were a number of questions in the vicinity of this question, is there sufficient is there a moisture level in biomass whereby one can assume that no explosion is possible per the NFPA? Meaning, is there a moisture level in biomass that renders it relatively inert and completely safe?
There is in the case of wood, green wood that has moisture levels at NFPA 664 uses as a threshold for when it can be combustible. I don't remember the exact number, but it's
25%, Bob.
How much? 20?
25% moisture.
25%, yeah. So that's an example there. I have not seen. It's too hard to generalize that for other biomass, and some people question even that thing on particle size. But that's the about the range where you can count on moisture to prevent combustibility.
If there's no one else that wants to add to that, I think I'm going to conclude today's webinar. Once again, big thanks to IEP. Big thanks to our presenters for a very, very rich technical webinar. Thanks, everybody, for joining us. If you're going to be in North Carolina next week, certainly say hello. If not, our next webinar in the BBI platform is a data webinar for Ethanol Producer Magazine, and that's April 28th. If you're on the phone and in the ethanol industry, be sure and register for that webinar as well. Thanks, everybody. Have a great week.